This lecture is about color image processing. So far in the course, we have considered that images have only one channel. This channel will represent the gray levels. For example, if we use 8-bit per pixel, 256 different gray levels, and that value will represent the amount of light or the intensity of light in every pixel. However, color is an important feature because it allows us to identify elements and objects in a scene that is beyond only the intensity of light. And the human visual system is able to see and distinguish millions of colors. So it is important for us to code or to understand how color can be represented in digital images. When we talk about color, we mean the visible spectrum of light. This spectrum is defined by the wavelength of the light that we perceive. So waves with this size around 400 nanometers to 700 nanometers we perceive as colors. So we have colors from violet to blue and cyan, green, yellow, orange, and then red. Wavelengths that are smaller than 400 nanometers are in the spectrum that we often call ultraviolet. If we decrease the size of the wavelength, we could reach, for example, X-rays and gamma rays. Those waves are so small that they can cross objects, and that's why they are often used, for example, for medical imaging. For waves that are larger than 700 nanometers, we have the infrared values or the infrared spectrum that range in between 1 millimeter to 1 centimeter and can be, for example, near infrared or far infrared, and those waves are associated when they are larger with heat. Larger waves can be associated with objects that we often use in our daily lives to, for example, to communicate. So radio waves and television waves can reach, for example, 1 kilometer. So those waves are emitted using a source of light. The most relevant source of light is the sun. So when we say we have the daylight, we have a spectrum that is similar to this one here on the top left hand side. So it transmits, or its response will change for the different wavelengths. So it is not uniform. The sunlight will, for example, have a response that is larger, or that is greater for wavelengths around the cyan and green than for deep blue or violet, for instance. This is different, for example, from a bulb or a light bulb of incandescent light. This type of light is much more warm, that we call, because it has a response that is more concentrated near the red value. The fluorescent light has this spectral response, so you can see that it has many peaks in different wavelengths. So that's why it feels kind of weird or different to us, so very unnatural to us. The halogen light looks more like daylight, you can say, but it is also warm light. And then we can have LED bulbs or light sources that can, in some way, be designed to emit more light in a given wavelength. So cool white LEDs will have this shape, while warm white LEDs will have this shape. This is important because, for example, in computational photography, we have to consider white balance, and this will guide the white balance. We have also to distinguish color from pseudo-color. So as I told you, color is always associated with the visible spectrum of light. So when we have, for example, a satellite image, so showing the visible spectrum of light, what we see is matches what we actually have in the nature, so what a human perceives. So the sea, for example, is blue, while forests are green, and mountains or rock is brown, and when we have snow or when we have clouds, they are white. On the right hand side here, I have a pseudo-color image. So this image has colors that are associated with metaphors that represent some data, but they are not real. When we look at the satellite, we cannot really see those images. And here what we have is an image that was rendered by taking measures or measures of temperature in those regions. So bluish colors are metaphors for lower temperatures, while red colors are associated with higher temperatures. So as you can see here in Mato Grosso, it's much more warm than in around here in between Argentina and Chile, when we have the Cordillera dos Andes. So this is a pseudo-color image. Those colors here are not, they are in the visible spectrum only because we made them so, but the actual temperature doesn't have a visible color. We can have color that we call achromatic light. So in this case, is a single attribute of intensity without color separator. So this is also called amplitude, and in this case the light doesn't contain any color or distinguished color, while the chromatic light is a selection of specific wavelengths that compose a color. In our eyes, we have cells that are responsible for sensing color. We have red cones. So cones are the names of the cells. Cones, red cones represent around 65% of the total of our cells. Green cones around 33%, and blue cones only 2%. So the RGB system is inspired in this three stimulus color sensibility of our eyes. When we talk about color, we can compose colors by mixing colors. So I'm just going back a little bit. So why we are able to perceive colors that are not red, blue, and green? This is because the combination of those three values will generate different colors for us, the perceived colors for us. When you have, for example, three colors that we call primary colors, so by using blue, yellow, and red, and if we use paint or, for example, crayons, and we mix blue and yellow, what we have is green. So we did that in the kindergarten, right? When we mix red and blue, this is purple, and red and yellow is brown. However, when we use those colors and we see that, for example, in the kindergarten, this is not an exact set of primary colors with respect to a general or more general color system. The primary colors that use paint are in fact cyan, yellow, and magenta. This can be understood as a subtractive model, because paint is made of pigments, and the pigments will absorb wavelengths and reflect the remaining ones. So when we see an object that is yellow, it is actually absorbing all wavelengths but the one respective to yellow, the yellow color. So more pigment means more absorption and therefore a darker color. So when we have a white object, it's actually reflecting all light in all the wavelengths. So we see that, or we perceive it as white, while a black object is absorbing all the wavelengths. So it's staying with these wavelengths, and it is reflecting none or very small quantity of those. And this is why when we are wearing a t-shirt, say a t-shirt, a white t-shirt, and in the heat or in the sun, we feel that is cool. And when we are wearing something that's made of a darker cloth, so as a black t-shirt, this black t-shirt will transform light into heat, and then we feel warmer. In monitors, TVs, and projectors, the model is not subtractive, because what we see are not actually pigments, but is direct light. So this model is additive, because by adding light in different wavelengths, we have a mixture of light. More light results in a brighter color, so it's the opposite of the subtractive model. In here, instead of making, when we increase the number in the previous one, when we increase the amount of pigment, we make a darker color. In the additive model, when we increase the light, we made a brighter color. So in this case, blue and green will produce cyan, red and blue the magenta, and red and green yellow. In cameras, we have an array of sensors that are sensible to red, blue, and green. In a regular camera, what we have is a mosaic of sensors that have filters that allow them to be sensitive in different wavelengths respective to green, red, and blue. So each color is defined by the real response measured and then afterwards interpolated from the neighbors. So in the left-hand side here, I have the actual sensor. So we have green, followed by red, followed by green, followed by red, for example. So this pixel here, this first pixel is actually just measuring real green, while the second one is just measuring red. How can we then obtain all RGB values? By interpolating the neighbors. So for the first pixel here, we have green that is real, and the red one is obtained by averaging or making another measure in order to interpolate red values, and the same for blue. So next, I'm going to talk about color models.